Okay, so this next concept is deceptively simple. It's really not that hard, but it is used in a lot of ways that make it worth its own short video just to make sure we really understand what we're doing here. So we have a topic called vector valued functions. And this is a topic in multivariable calculus. Essentially what you're doing here is you're going to define some function, which we usually use r. It's going to be defined as a real value of some sort of parameter. So in this case we have t. Now this function r is a vector. And then the components of this function are some function of t for our x component, and then some function of t for our y component. And then if we have a k component, we have a k component. In this case, we'll just focus on 2p's. So what this says is that I have an input value of t, and I have a function that takes that input value and gives me some output value, and that is my x component. And then similarly, I have a different function that takes that same input value and gives me some other output value, and that's my y component. And those two components make up the vector r. So that's what we're saying here. So let's just say, for example, we have f of t, which will equal, let's just say x, or sorry, we're doing functions of t, not x. So we'll do t squared, and then we'll have a function g of t, where we're just going to have t minus 2. Okay? So the way we're going to rewrite this is we're literally going to plug this f of t in where this f of t is, and we're going to plug this g of t in where this g of t is. So this same vector is now, with this new definition, t squared comma t minus 2. But it is still a vector. We've still got our angle braces here. So make sure we're careful with that. Now let's say, well, I think that's cool, but what happens at the very beginning when time is equal to 0? What's going on in this vector? Where is this thing at, right? Okay, well, it's pretty straightforward. All we got to do is just plug these zeros in. So we're going to plug in 0 to t squared, so we get 0 squared. And then our other piece here is 0 minus 2, right? So we know that this is just going to come out to be 0 comma negative 2. So the vector is at 0 comma negative 2 when time is 0. So it has a magnitude of, what is that, 2 squared and then square rooted, so that's just going to be positive 2, so magnitude of 2, and then this is going to be the thing that tells us our direction, right? But let's say, okay, well now I want to know what is going on when time is 1. Well, so let's do 1 squared and then 1 minus 2, and I know this isn't super complex yet, but trust me, it can be tricky. So now we have 1, negative 1, right? But remember, this is still a vector. This is not a point, this is a vector, okay? So that's where it can get a little tricky, is people like to think of these as points sometimes. And while you can use the information from it to tell you stuff about a graph, they are not points, they are vectors, okay? I just pulled a quick example off of one of the textbooks I use. So let's just knock out this guy real quick, just to give us some practice plugging in our numbers with some constant scalars and stuff. So in this case, we're going to start by doing r of 0 of this vector that we have listed here. Notice this one's in I and j format. That's totally fine. We can do it in angle brace format. That's also totally fine. So I'm gonna use angle brace format just because it's what I'm the most comfortable with. So we've got 4 times cosine, and now we're going to plug that 0 in everywhere where we see a t, and then we've got comma 3 sine of t, which is 0 in this case. So we already know cosine of 0 is 1, but sine of 0 is 0, so this component goes to 0. So we know our vector valued function at t equals 0 is going to come out to equal, cosine of 0 is 1 times 4 is 4, and then this all goes to 0, so we're just going to say 0. So our vector value function at 0 is equal to 4 comma 0. Okay? And then the next one we're going to do, we're just going to do pi halves. So we've got 4 cosine of pi halves, comma 3 sine of pi halves, angle brace, still a vector. Okay, we know cosine of pi halves is 0, and we know sine of pi halves is 1, so this one's going to kind of be a little bit of the opposite. So in this case, we're going to get 4 times 0 is still just 0. 3 times 1, however, is 3. okay? And then we can do this 2 pi thirds real quick, just to do it. So we've got r, and then 2 pi over 3. So we've got 4 cosine of 2 pi over 3, and then 3 sine of 2 pi over 3. Now, this one's a little more tricky because pi over 3 is one that not everyone always remembers, and 2 pi over 3 is already even weirder because now we're in the second quadrant, right? So I wouldn't normally go into this detail on the trig in a video that's not trig related, but just as a really fast explainer of what I'm doing, I know that 2 pi thirds is here, right? So I know that that's 2 pi over 3, and I know that it's going to have the same y and x value as whatever I get on this side. So instead of doing 2 pi over 3 over here, I can just take pi minus 2 pi over 3, which will give me just pi thirds, and I can just take my values off of that and flip the x. Okay? So if I have 2 pi thirds cosine, I need the x for pi thirds, which we already know is root 3 over 2, and then, like I said, we're going to flip the x, so we've got negative, and then we still have our 4. Okay, and then we have 3. Now sine of pi thirds is going to be 1/2, so that's 3 times 1/2. Oops, that's not a parenthesis, that is an angle bracket. Okay, and now I'm going to delete this little graph I did just to illustrate that point so I can finish writing this out. So now we just have negative 4 divided by 2 is negative 2 root 3, and then over here we have just 3 over 2. Okay, and that is pretty much our answer here. So this is the really quick way to just understand how to plug things into vector valued functions. You can also deparameterize these to graph them. In fact, this A example I grabbed conveniently works pretty well to illustrate this point as well. So let's go ahead and do it real quick. So I'm going to do two things here. I'm going to write a quick little chart here where we're going to have t, and then we're going to have x, and we're going to have y. Okay, those are the things I need to find based on this, this vector valued function we were given, which I'll rewrite right here. So we're going to have r of t is equal to 4 cosine of t, comma, 3 sine of t. And it's a vector, not parentheses, angle brackets. Okay, and the other thing we're going to want to do is we're going to graph this, just for funsies. Okay, so in order to deal with this, I have to first deparameterize this so I kind of know what's going on, right? You don't have to do this to solve it, but it's just to really understand if we're going in the right direction while we're learning. Once you know that you've got it pretty much under control, you can just go into plugging in some values and then graphing those values. But either way, we just want to make sure we know what's going on. So what we can do is we know we have a cosine here and a sine here, and we're in t, we want to get to xy to deparameterize this, right? Well, we know a thing that deals with cosine and sine and makes those go away to give us just x's and y's. And the thing we know is that if we have cosine squared plus y, or sine squared, sorry, we'll get 1. Doesn't matter what the angle is as long as the angles are the same. So I'll write, I guess, theta just in case I confused anyone there. Okay, so I know I want x's and y's, and I know I want this relationship. So why don't we say let's let x equal that 4 cosine of t, and then y will equal this 3 sine of t. Sine of t, thank you. Okay, and so now what we can do is we can look at these and say, okay, well, that's all well and good, but I don't really see how that helps us quite yet, right? Because this is still two separate things that we're dealing with. Well, let's go ahead and put this into this form where we have x plus y equals some form or something over here. We know we kind of want to go for 1, right? Well, all we have to do to match this form and this form is just square everything. So let's get x squared equals 16 cosine squared t, and then I kind of ran out of space, so I'll do y squared over here, so we get 9 sine squared of t, right? And so now we should have everything we want to plug into here. All we have to do is square these guys, right? So we have a problem though, because if right now if I go and I say, let me create a little space and we'll just do this all together so it makes more sense. So if I go right now and I say, okay, well I have 9 sine squared of t and I have 16 cosine squared of t, well, I don't really see how I can plug that into this, right? That just doesn't make sense right now. So all we have to do is move this constant over and we'll be able to make this work, right? So we'll just divide this one by 9 and we'll divide this one by 16. And now we should have a form where when I say sine squared and cosine squared and I plug those in, I now get x squared over 16 and y squared over 9. Now what the heck kind of graph is that? If you don't immediately recognize that graph, that's actually going to be the graph of an ellipse. Okay, but this is kind of the function that we should be looking to see. So we should see some sort of elliptical graph. So now let's go to our chart and start plugging stuff in and see if that is indeed actually what we get. So what we're going to do is we're just always going to pretty much start at 0, because why the heck wouldn't we, right? Start at something easy. Okay, so when I plug in 0 here, my x component, I get cosine of 0, which is just going to be 1 times 4, so I get 4 in my x component. In my y component, I'm going to get sine of 0, which is 0, so that's just 0. Well, let's do easy values that we know, right? So this t isn't being multiplied by anything, so we can just use our first couple unit circle values. So let's use pi thirds and pi quarters and pi sixths and pi halves, which now that I'm saying this out loud, I realized I made a mistake over here. This should have been, actually, okay. I made a mistake in the explanation, but I used the right numbers. Just a really quick aside so I can fix that explanation. So when we had this guy here, which was 2 pi over 3, the angle that finishes that is pi over 3, but this actually corresponds to pi over 6 on this side. Well, maybe it doesn't. I'm going to have to think about that. I'm going to edit that out. Okay, so like we were talking about, we're going to keep solving this guy out. So when we plug in, I guess let's zoom out just a hair. So when we plug in pi thirds to cosine, this is going to be where cosine is at 1/2. Now we have times 4, so 1/2 times 4 is just going to be 2. And then we can do the same thing with sine. So we're going to get root 3 over 2 times 3. So we get 3 root 3 over 2. Now we get pi quarters. They're going to be the same for both. So we have 4 times root 2 over 2, which is going to be 2 root 2 over 2. And then 3 times root 2 over 2 is 3 root 2 over 2. Nothing special there. Pi 6, the x's and y's basically flip, except we have different coefficients. So 4 times root 3 over 2 is just 2 root 3. And then 3 times 1/2 is just 3 halves. And then for pi halves, cosine is going to be 0, so we get 0 here. And then sine is going to be 1, so we'll get 3. Okay, and I'm going to do just 2 more points just to make sure we can really see what this is going to look like. So we're going to do pi and 3 pi halves. Okay, so at pi, cosine of pi is -1 and sine is 0, so we're going to get -4 and we're going to get 0. And I think we can see where this is going. We're going to get 0 and -3. If you don't believe me, you can double check. Okay, so now we should have enough points to graph. So it's important that we started at t equals 0 for a couple of reasons. Really, the biggest thing here is that we want to make sure to start at t equals 0 because this is going to tell us what direction our graph is going, which is the cool thing about vector valued functions. Because they're parameterized, they also tell you the direction of the graph, which can be really useful, especially in something like physics. So at t equals 0, we have x of 4, which is here, and then y is 0. So we've got this point. And then we're going to go pi thirds is going to be 2 on x, and then root 3 over 2. So root 3 we're expecting to be somewhere around 1.4. So then 3 times 1.4, we'll call it like 4.2-ish, divided by 2 is like 2 point something. So we'll say it's like kind of right there-ish. Why not? I got the same value. Oh no, that's 3 root 2 over 2. So that one's going to be just a little bit higher, but not much. And then we know the next one we have is 3 over 2, which is exactly 1/2 on the y. Did I do that right? Oh, you know what? I'm realizing now. We accidentally went out of order because I wrote the angles out of order. So we should be here, and then this one should be here. There we go. That makes more sense. Okay. And then pi over 2 is at 0 on x and 3 on the y. And then we can just look at our other two values real quick. So we got our -4 here and our -3 here. So now if we draw a decent looking graph, which I'm not great at, but the tablet is, we can also see, okay, we got that kind of ellipse shape we were looking for. That's awesome. And then we also can look and say, oh, hey, you know what? We started at 4, 0, and then we went to 0, 3. So we must be going in a counterclockwise direction. Okay? The other thing we can do if we want to just kind of quickly double check this, since we went and found our xy formula, we know that for an ellipse, this bottom part tells me my x-intercept and this bottom part tells me my y-intercept. So here I've got 16, so I should be at plus and minus 4. And here I got 9, so we should be at plus and minus 3. And that's it. That's a quick introduction to vector value functions. The next thing I'm going to work on in the next video is going to be vector valued functions and calculus on those functions.